This conference will now be recorded.
Hello students, welcome to the PUIQ discussions which we have started for JEE Mains papers. So today we have questions from
This conference will now be recorded.
Hello students, welcome to the PUIQ discussions on JEE Mains paper.
This conference will now be recorded.
Hello students, welcome to the PUIQ discussions on JEE Mains papers. So we have been solving numerical problems from JEE Mains paper. We have already almost completed this 2020 paper. So today we have got few numerical problems from SIP 2 4th September paper. So let us try to solve all these questions. So the first question here says a circular coil has moment of inertia 0.8 kg per meter square. Moment of inertia I is equal to mr square, so kg meter square around any diameter. Okay, for a circular coil, so moment of inertia is given. Okay, I is given, and this is about any diameter. Okay, kg meter square, and is carrying current to produce a magnetic moment. So it is carrying certain current. So if a circular coil carries a current, suppose current is in the anti-clockwise direction, then the magnetic moment direction will be along this way. Okay, if I write that m, okay, m vector, and m is given by I into a, so that value, magnitude of that is given actually. Okay, let me write the magnitude small m, which is 20 ampere meter square. So the coil is kept initially in a vertical position. As you see here, this is the vertical position, and it can rotate freely around a horizontal diameter. You can see this diameter. Okay, so you suppose this is horizontal diameter. Okay, so it can rotate about this horizontal diameter. When a uniform magnetic field of 4 Tesla is applied along the vertical, see this is 4 Tesla which is applied along the vertical, it starts rotating around its horizontal diameter. Okay, around this horizontal diameter it rotates. Okay, that means when it rotates, I can take various projection of this magnetic moment vector. Okay, I have initially, if this is, suppose the current is flowing in this way, then according to thumb rule, the magnetic moment direction will be either this way. Okay, or if you take the direction of the current in the opposite direction, it will be like this. Okay, so you look initially, this is actually, so if I say this is the magnetic moment direction, this is the magnetic field direction, initially they are perpendicular to each other. So this is 90 degree initially. Okay, magnetic moment direction, magnetic moment and the magnetic field, they are perpendicular to each other. The angular speed the coil acquires after rotating by 60 degree. After rotating by 60 degree, it acquires certain angular velocity. Okay, so that angular velocity you have to find out. Okay, so this problem can be solved See how what you can think, what all you can think. I know magnetic moment, I know magnetic field. So magnetic field is making certain angle with magnetic moment, or magnetic moment is making certain angle. Initially it is 90-degree, and we have to see we have got a configuration where magnetic moment is making an angle 60-degree with B. So with this, what we can think of, and also it is rotating. See, this problem can be solved by conservation of energy. Okay, applying conservation of energy, total energy. Okay, applying conservation of energy. Of energy. All right, so let me change the ink. So initially, look, initially it was at rest, actually vertical position at rest. Okay, so what will be the kinetic energy? Here we will be considering the kinetic energy, and that kinetic energy is actually rotational kinetic energy. Anyway, it is not translating anywhere, it is just rotating. So we have to consider, see, initial potential energy plus initial kinetic energy is equal to in final potential energy plus final kinetic energy. So final kinetic energy, see, moment of inertia is given about diameter. So we have certain informations given if we require for calculating rotational kinetic energy. You know, rotational kinetic energy K rot, rotational will be half I omega square. Okay, see, initially this is also 0 and this is also 0. Kinetic energy, both kinetic energy and potential energy 0. Why potential energy 0? See, magnetic potential energy for this magnetic moment. See, when a magnetic moment is in a magnetic field, it will actually acquire a potential energy. In general, the expression for that potential energy is minus m dot b, m dot b, or minus, so minus mb cos of the angle between them. Okay, this is the potential energy. As I said, initially magnetic field and the magnetic moment will have an angle between them is 90-degree. So initially potential energy will be 0, right? If cos 90 is 0, then potential energy initially will be 0. So that's why these things are 0. So what is the final potential energy? We have been given a configuration. See, theta is equal to 60-degree. So what will be the final potential energy? That will be minus m b cos of 60-degree. Okay, so what is this m? M is given 20. Okay, what is b? B is given 4 Tesla, and this is cos 60-degree is actually cos 60-degree is half. Okay, cos 60-degree is half. So let us write this cos 60-degree. Cos 60-degree is half. So this will give you certain values. Okay, so this is 40. Okay, minus 40. This is in terms of energy. If you write this unit, so it may be written in joule. Okay, then this potential energy, now we have to find out what is kinetic energy. So kinetic energy, final kinetic energy, let us say the angular speed or angular velocity, we should say angular speed only, angular speed at this 60-degree angle is omega, then I can write half I omega. Okay, omega square, half I omega square. So this is equal to actually UF. All right, so Kf is equal to UF from the conservation of energy we are able to get. So u square is equal to, sorry, omega square is equal to 2 uf divided by I. Okay, let me first find out what are these. 2 u is given as 40. Okay, I'm taking the magnitude only here. Yeah, so both I have to bring other side, right? So this will be 2 into 40 divided by moment of inertia is given as 0.8 kg meter square. So 0.8 over here. Okay, so what we get? See here, this will be 800, right? 8 into 100 divided by 8. So look this, omega square is equal to 100, so omega will be 10, right? So this is actually 10. So omega is actually 10 radian per second. I hope you have understood this. If you are not able to understand, let me draw some figures of rotation of this. See, sometime it will be like this. Okay, this one. Okay, this loop will be like this. So moment of inertia, sorry, this magnetic moment will have some other direction, right? So so this will actually make your magnetic moment direction changed. Okay, and this is rotating, you know. So magnetic moment is actually depending on, so this one, if this is the plane, as I said here the figure is, so it will be actually perpendicular to the plane of the loop. Okay, and also it will be actually determined by thumb rule. So if you just imagine a little bit, you'll be able to see that this magnetic moment is making different angle with the magnetic field at the when it is actually rotating. Therefore, option B will be the correct answer for this question. Okay, let us go to the next problem. So this problem says a paramagnetic sample shows a net magnetization. So net magnetization M, capital M, is given as 6 ampere per meter. When it is placed in an external magnetic field, B is equal to 0.4 Tesla. So what is the information? Okay, some more information about it. At a temperature 4 Kelvin. So when the temperature is 4 Kelvin, at 4 Kelvin temperature, when a paramagnetic sample is kept in this 0.4 Tesla magnetic field, then the developed magnetization developed in that sample is 6 ampere per meter. Now another situation is when the sample is placed in an external field is given 0.3 Tesla and temperature is given as 24 Kelvin, then what will be the magnetization? Okay, so let us say these are all 1 and these are all 2. Okay, so this is actually problem from simply Curie's law or Curie law, we can say. So for a paramagnetic sample, we know paramagnetic susceptibility is C by T. Okay, C by T, or we can say, see this chi is equal to actually chi is m by h. M by h is equal to chi. Okay, m by h is equal to chi. Since so let us just put, since we have been given b instead of h, so we'll multiply. So b and h, they have a relationship, b is equal to mu 0 h. So if we want to find out what is h in terms of b, so b by mu naught. Okay, mu naught. So therefore, see, we can actually say, okay, let us write this here itself. So we know chi is equal to m by mu. Okay, so b by mu, m by h means b by mu, so mu naught will be multiplied here, and this will be b, that is equal to c by t. Okay, c by t. So this constant is actually same for both. Okay, and this mu naught is also a constant term. Therefore, I can somehow write this m by b, or m is directly proportional to b and inversely proportional to c with a constant term k, where I have multiplied or divided. Let us say we divide both sides with mu naught, so this constant will be some different constant other than Curie constant. So I can write m is equal to kb by t, or in other word, it is directly proportional to b divided by inversely proportional to, so inversely proportional to temperature. So I can write m2 by m1. M2 by m1 is b2 by t2, and it is t1 by b1. Okay, so t1 by t2 and b2 by b1. Okay, b2 by b1. Let us see now what are the informations given. So we have been given B1 as 0.4 Tesla, B2 as 0.3 Tesla, temperature T1 is 4 Kelvin, and temperature T2 is 24 Kelvin. So T1 is 4 Kelvin, this is 24 Kelvin, and this B1 is, this B2 is 0.3 Tesla, and B1 is 0.4 Tesla. Okay, so these two I can. Okay, let us do the simplification, that's all. So so 3 8, okay, so I think there will be, right, all right, so this is 4, so 1 over 8, let me check. I see, so m1 I have to multiply again, so this m2 is equal to m1 divided by 8, so m1 is 6, this is 3, this is 4, so this will be 0.75, so m2 will be 0.75. So here the last option will be the correct answer for this question. Okay, now we'll go to the next problem. So this problem says, a series LR circuit is connected to a battery of EMF V. If the circuit is switched on at t is equal to 0, then the time at which the energy stored in the inductor reaches reaches 1 over n times of its maximum value. So you have to find out the time actually. Then the time at which the energy stored in the inductor reaches its maximum value. Sorry, 1 over n times the maximum value. Okay. So how to solve this problem? First of all, you have to identify this problem. This problem is not from AC LR circuit. This is actually from DC LR circuit. Okay, DC LR circuit. LR inductor and resistor, DC LR circuit, and it is actually, this is L, this is R, so this is V. So it is a transient phenomena. That means, in the circuit the current will be gradually increasing in LR circuit. So the current equation will be I equal to I0 into 1 minus e to the power minus R by L into T, where R by L, this is actually time constant. So this is the equation which you should remember. This is the equation in the so current equation. So at any state of time you can get the current from here. All right. So now again we know the power stored or the energy stored in the inductor. Energy stored in the inductor is L is equal to E is equal to half, here mu will be there, then L I square. So what is the maximum current? So at the given instant, see, at the given instant, let us say at that instant is t. So at the given instant, the energy of the inductor circuit will be half mu 0 L I square, which is 1 over nth time the maximum value. Maximum value will be half mu 0 L I0. I0 is the maximum current. So when the maximum current is reached in the circuit, the energy stored by the inductor will be the maximum. So this L0 is the maximum current in the circuit. Okay. So from here, look, this term can be cancelled out. So what we have here is actually, I can find out what is I by I0. See, I by I0 I will be able to find out, that is 1 over root over n. This is the information I can extract out from this information given here. Okay, 1 by n times the maximum value of the current, maximum value of the energy stored in time t, let us say. And see, what is the I by I0 ratio at time t? At time t, current will be I is equal to I0 1 minus e to the power R by L, it is for minus R by L into T. So this is what the ratio of this I by I0 will be 1 minus e to the power minus R by L into T, right? So this is, say, the equation number 2, and this is equation number 1. Okay. So if we equate these two, okay, if this, okay, from equation number 1 and 2, I can equate them. Okay, 1 minus e to the power minus R by L into T, and that is equal to 1 over root over n. Okay, so I need to find out the time from here, right? So what I can do, I can write 1 over 1. Okay, so this is equal to e to the power L by RT. This I am just reversing here. Okay, so now I can actually do a little bit of simplification from here. See, look, I'll go for another page maybe, or let me get this page. So what we have? We have e to the power L by RT is equal to root over n minus 1 divided by root over n. Okay, right? If we take this like antilog, then we will have L by RT is equal to ln root over n minus 1 divided by root over 1, sorry, root over n minus 1 divided by root over n. Now I need to find out, see, I can actually reverse this. So I have to find out t, right? So t, I'll take this side, then I'll have r by l and ln root over n by n root over n minus 1. Okay, so this is what I'll get. Let us see what are the options given here. Root over n, L by r, root over n divided by root over n minus 1. So option C is actually correct for this question. Okay, so this will be correct answer for this question. Let me look whether we have got the same thing. Yes, so T is equal to L by r ln root over n divided by root over n minus 1, this one. Let us see the option C. Yes, the same option we have got here. So this C is the correct answer for this question. All right, so this was actually from transient phenomena of current and voltage of DC LR circuit. Now we'll move on to the next problem. This problem is also very interesting. This is very familiar problem. Like the type of the problem is very familiar to us, but with a little twist, not even a twist, but little extra information we have here. See, the electric field of a plane electromagnetic wave is given, and that is E vector is equal to E0 x cap plus y cap sine kz minus omega t, right? This is the electric field. So what will be the magnetic field? See, here there are different options given. The first option I can actually readily cancel, because if the electric field is given as sine kz, magnetic field also will be given in terms of sine kz only. Okay, let us check with the other options. How do we do that? See, this magnitude is 0 by c and all are same, so I'm not going to do all those things. Only thing is this one. Okay, what we have to check, this unit vector. Okay, so by doing this, we are saying that the electric field is actually, say, electric field and magnetic field will oscillate perpendicular to each other, right? So suppose this is z axis, so because we know from this equation we can say that the wave is actually propagating along z axis. Suppose, okay, so let us say this is z axis, this is, okay, let us say this is z axis, okay, this is z axis. Okay, I think I'll redraw this. So the wave is as a whole oscillating in this way, okay, or sorry, propagating in this way. So this is z, positive z direction. This is suppose positive y direction, and this is positive x direction, or ulta. I'll take the horizontal direction. Let us say this is x and this is y. See this electric field where it is oscillating 1 from, see, 1 unit from x, 1 unit from y. So what is the position? See, position is somewhere here, right? So it is actually moving along this way, right? So if this is the electric field, my magnetic field has to be actually perpendicular to this, okay? Perpendicular to this. So what is the possibility? Possibility can be this one, this way, where it will be where it will be 90°. This will be another possibility is this way, where it will be 90°. Okay. So these are two possibilities of my magnetic field direction. Okay, along which magnetic field can oscillate. Now we have to check what is the correct possibility. Okay, one is see this is along x, positive x minus y, or minus x, x positive y. Okay, so that thing we have to check. Okay, this option seems no change with this. Okay, I think I have some printing mistake over here. We can cross check the question. Let me just see. But anyway, before that, we can just conclude this. So how do we conclude? We can conclude that, say, E cross B will be the direction. What is the direction here for the wave vector? So wave vector direction is actually positive z cap. Okay, so we have to actually better to go with this cross product. You know, you can use the cyclic rule, x, y and z. Okay, look, if I take, see, this x minus y and x plus y is e. Suppose x plus y, x cap y cap cross x cap minus y cap. If I take this, see, x cross x will give you 0, x and y, y will give you z with a minus sign here. So yx, again, yx will give you xy, yx. Okay, sorry, yx will give you minus z. So I am getting ultimately minus 2z cap. That means it is indicating that the wave has to be propagating in the negative z direction. So this option is not correct. Okay, this is actually showing phase change, so this is not the correct one. Okay, so this is also wrong. Now I have these two options. Anyway, this option is same as this. I think there will be some changes. I'll show you the questions. What is the real question? I have to see these options, but let us check with this option. Okay, so if I have this x plus x cap plus y cap, and cross product x cap, sorry, minus x cap plus y cap. See, this will give you 0, then x, y will give you z, x cap y will give you z, and then y minus x. So y x will come minus, but you will get anyway plus because there is a minus sign over here. So z cap it will give you 2 z cap. Okay, the last one will be 0 anyway. So 2 z cap. So this is actually indicating you that the magnetic field must be this one, so that you get the whole wave propagating in the positive z direction. So this is the answer. Let me see that the last option, what was the correct one. I think I have this here. Oh yeah, so I have this question here. Let me cross check. Yes, the last option was, yeah, this is even. Okay, this is minus, plus. Okay, this should be plus actually. Okay, this should be plus x plus y. Okay, this should be plus sign over here. Okay, so anyway, we have got the right answer here. The option C will be the correct answer. All right, so option C will be the correct answer over here. Let us go to the next problem. So this problem is from modern physics, photoelectric effect experiment. So the question says, in a photoelectric effect, the experiment, okay, so in a photoelectric effect experiment, the graph of stopping potential V versus the reciprocal of the wavelength obtained is shown in the figure, and the intensity of the incident radiation is increased. Graph does not change. Sorry, this will be changed. Okay, this is written in charge. This should be changed. Okay, does not change. Change. Straight line shifts towards left. That means the graph will come like this. The straight line shift towards right. That means it should go like this. If okay, so as the intensity increases, okay, intensity increases, the slope of the straight line get more steeper. That means, you know, it is like this, so you must get like this. Okay, this is more steeper. Okay, so whether it will shift towards left if the intensity is increased, whether it is going rightwards, or the curve will be more steeper, or there will be no change in the graph. Okay, so what is the answer for this? You look, if we draw, okay, see, this is actually stopping potential. Let me write down the photoelectric equation given by max, maximum kinetic energy of the emitted electron, okay, is equal to the excess energy. Suppose if nu is the frequency of the incident photon and work function is phi, okay, work function phi actually indicates the threshold frequency also. Let me write that as, if the threshold frequency is nu prime, okay, threshold frequency is nu prime, then this can be written as h nu prime. So h nu minus h nu prime. Okay, this is k max, maximum kinetic energy of the emitted electron. Now, stopping potential means if you have already cathode and you have anode here, you have to give some reverse potential such that the emitted electron does not reach to the anode. Okay. Okay. So if you want to do that, you know, you have to actually decrease the energy. Somehow you have to decrease or lose the energy of the emitted photon. Okay, see, how do you decrease this energy of the emitted photon? So 1 over lambda has a dimension of nu only. Okay, dimension of nu. So as the nu increases, what happens? Nu increases means this one. Okay, as the nu increases, that means the energy of incident, like incident energy increases, then obviously this k max will be greater. So k max also will be increasing linearly. So this is k max, maximum kinetic energy emitted, kinetic energy associated with the emitted electron. Okay, so what about intensity? Intensity means the current will increase, more number of photons you will get, more number of electrons. So more intensity means more photons will knock more electron, but this there is no change in this case. Okay, there is no change in the incident energy if you increase the intensity. Okay, so then this intensity is actually independent of the so stopping potential, okay, stopping potential is independent of independent of intensity of light, intensity of light sorry intensity of light, incident light. Okay, intensity of incident light. So therefore here graph should not be changing. Okay, it should not change actually. Okay, the graph should be the same if the incident radiation, intensity of the incident radiation is increased. Okay, now we'll see the last question for this session. So this question says identify the operation performed by the given circuit below. So you can see this is actually not, see, this is OR and there is not operation. So you'll get from here A naught from here, and also the inputs are actually sorted, so you'll get a single input. So B naught here. Okay, B naught. So not B means A bar and B bar. You get here. Similarly, C bar also here. So this is OR and then NOT. So this operation will be A bar plus B bar plus C bar whole bar. So if we use De Morgan's theorem, this will give you this. So this will make the output, final output, A and B and C. Okay, so it will actually be giving you finally and get. So this was a really very simple problem, and don't get confused with the, see, we know this De Morgan theorem for double input. Okay, for double input we know it will be this and single like individual bar. We know for 2 units, so this will be A or bar, A or B. Okay, so we know for two input circuits, but this can be applicable for the three input circuits as well. Okay, so therefore it will be AND gate rather than NAND or not gate. Okay, all right, I'll stop it here for today. Next day or in the next session we'll be completing this year's question papers. All the question papers will be covered by another class, and then we'll catch up with the 21 question. Okay, thank you.